Swayam Prabha. Digital India. Educated India.
Hello students, in today's lecture we will be discussing catalytic nanomaterials for environmental degradation, where we will be discussing in detail catalysis chemistry, activation energy, degradation mechanisms, adsorption types and experimental fitting data. So environmental pollution is basically polluting of the soil, water and air by various contaminants that cause pollution. This is because of rapid industrialization. Industries released wastewater into our environment, which leads to persistent pollutants. So these pollutants persist and make our environment toxic. So conventional remediation methods are often not enough. So nanomaterials have revolutionized the environmental remediation process because of their high reactivity and larger surface area. So catalytic nanomaterials basically they have provided a sustainable solution to this problem. As a collective sustainable intention is required to inhibit this pollution menace that is affecting our environment. So that is how rapid industrialization and pollution has polluted our environment. Factories, vehicles and waste dumping, these lead to air pollution, water contamination and soil pollution. And then catalytic nanomaterials for remediation. You can see that conventional remediation methods have not been enough. They have been used for a while, but they are not enough. The chemical treatment, the filtration systems and the soil excavation, these are all costly and inefficient and of limited effectiveness. But catalytic nanomaterials for remediation, these are nanocatalysts, they have provided some sustainable solution, that is a cost effective solution. They are highly efficient, eco-friendly and cost effective. So these can degrade pollutants, these can either degrade pollutants or remove pollutants and purify our environment, either water, air or soil. So that is these nanomaterials are basically advancing environmental cleanup. So water can be contaminated by bacteria, pesticides, heavy metals, solvents, oil spills vagera, these cause pollution in water. And soil can be contaminated by food waste, chlorinated compounds, heavy metals. So soil is contaminated by all these. And air can be contaminated by various gases, carbon dioxide, ammonia, carboxylic acids, aldehydes, nitric oxide. So all these things contaminate air and this is pollution in entirety. So how are we using catalytic nanomaterials for remediation? We are using all these methods. So they can be used in filtration, they can be used as chemical reactions where either dechlorination, reduction, oxidation reactions with these non-toxic, less toxic bioproducts are formed and certain pollutants are degraded by chemical reactions. Then all these things I will be discussing in detail later. Then photocatalysis, where nanoparticles are put on a supporting material and they basically adsorb basically the pollutants adsorb to this catalyst and light strikes here, UV light breaks down the adsorbed pollutants and final products are desorbed. So that is photocatalysis. This I will be discussing in detail in my later slides. So they can be a basic adsorption, just a simple adsorption, they just adsorb and eliminate. So our nanocatalysts are going to adsorb the pollutants and make them in a bigger size, like this basically happens with the nanoplastics and nanopollutants. Your nanocatalysts are going to bind with them, aggregate them and make it in a bigger size and eliminate them. Or sorbents, that is the contaminants this can be with the help of sponges. You can remove pollutants with the help of sponges. You can coat your sponge with some certain metal nanoparticles that can help to remove the contaminants from water. This can help, basically this can help a lot in water remediation processes. So this is how various nanocatalysts use various techniques to remove water, soil and air pollution. So catalytic nanomaterials, what are they? They are exactly nanomaterials that accelerate chemical reactions. As the name suggests, as catalysts are inherently, they just accelerate chemical reactions by lowering the activation energy of a reaction. So what catalysts do? They lower the activation energy of a reaction, the energy that is required for the reactants to turn to products. Okay, so this process is sped up by nanomaterials. Every catalyst basically does that. So our catalytic nanomaterials are basically catalysts. So what are they doing? They are lowering the activation energy of the reaction and speeding up the reaction process. So nanomaterials that accelerate chemical reactions, these are catalytic nanomaterials. So they have a large surface area and abundant reactive sites, as you already know that smaller the material, larger surface area and more the reactive sites. So that means more adsorption and better adsorption and better catalysis. So they lower the activation energy more efficiently than the bulk catalyst. So they can lower the activation energy better than the bulk catalyst. So this is being widely used, this property is being widely used for pollutant degradation. So this is how they speed up the degradation process and also by adsorbing to the pollutant. So what is the difference between natural enzymes and nanozymes? Natural enzymes, basically your nanozymes are mimicking the natural enzymes. So you already know that natural enzymes are basically catalysts. So our nanozymes are also catalysts and these are mimicking these natural enzymes. Like this is a nanozyme, a carbon dot, which mimics the activity of horseradish peroxidase enzyme. So this is going to mimic the peroxidase activity of this enzyme. What is this enzyme used for? Horseradish peroxidase enzyme. Basically this is an enzyme that that breaks down hydrogen peroxide. So it is known as horseradish peroxidase enzyme. So its peroxidase activity is mimicked by carbon dots that are nanomaterials. These are nanozymes. So these mimic the catalytic property of this and break down hydrogen peroxide in the similar fashion. So these basically mimic these. What are the advantages? See, for natural enzymes, there is a higher catalytic activity because enzymes are highly specific. So the advantage is that they have a higher catalytic activity than any nanomaterial. So obviously because they are specific to their substrate, so enzymes are basically, they contain they have this advantage over any nanomaterial, that they are basically superior in terms of biocompatibility and higher catalytic activity and also higher selectivity. They are highly selective, the enzymes they are highly selective. But with nanozymes, what are the advantages? That there is a long term stability. Okay, it is very hard to maintain natural enzymes on a day basis. It is very hard. You need particular temperature, you need a particular pH, enzymes degrade very fast and so it is not very cost effective and simple to maintain the enzymes. So for long term stability, nanomaterials are a much more better option to use if they are doing the same thing. So and reusability, nanomaterials can be reused while enzymes cannot be reused. So nanomaterials win over nanozymes this way. Then recyclability, nanozymes basically they can be recycled also, but nanozymes, natural enzymes cannot. And nanozymes, they have more resistance under extreme conditions. Like with high pH and temperature, they can easily tolerate these temperature and pH fluctuations. Nanozymes, these can tolerate these fluctuations, but natural enzymes, they cannot tolerate that much of fluctuations. Okay. Then there is easier immobilization. There is easier immobilization for nanozymes, but with natural enzymes, it is not so. Disadvantages is that natural enzymes basically they are expensive and their method of synthesis is highly complex. As you already know, that is difficult to synthesize enzymes and it is also an expensive process. And for environmental remediation, which is such a huge problem, you cannot be using such expensive methods on a larger scale. So that is a disadvantage. Then it is difficult for storage also, as you know that they require specific temperatures in pH. So, you have to maintain those, so it's difficult to maintain that, more there will be more energy consumption, cost consumption for maintaining. So, their storage is very difficult. Then the ease of denaturation, they easily denature, slight changes in temperature and pH and the enzymes are denatured. So, these are the disadvantages that are associated with natural enzymes. But with nanozymes it is not, but there are certain disadvantages with our nanozymes also, like surface modification is required to enhance the performance. So, catalytic nanomaterials also need some surface modification, like you need to add certain functional groups to their surface for them to for the required performance, like whatever you want them to do, they will need some surface modification with that. So, that will need some chemical reactions to enhance their performance. Then some nanomaterials might produce cytotoxic byproducts. So, as nanomaterials are, you have been synthesizing nanomaterials, so they might also produce cytotoxic byproducts. So, that needs to be kept in mind while you create some nanomaterial for environmental remediation, because you cannot be creating more toxic materials to degrade some toxic materials. So, that is something that you keep in mind. Defect engineering of nanomaterials for catalysis. So, by now you know that nanomaterials have a lot of surface defects because they have a very high surface area. So, the surface defects are also in a much bigger quantity. So, the surface defects basically pose certain challenges, as well as they also offer certain prospects. So, challenges means you need to control certain defects because it affects the stability and durability of the materials, and it also challenges are in the characterization and understanding of the catalytic activities. And prospects are that the catalyst can be multifunctional and sustainable and efficient catalysis can be possible, tailored selectivity and enhanced catalytic performance. So, you can tailor selectivity of a nanomaterial by intentionally creating defects on its surface. So, you can tailor the selectivity and enhance the catalytic performance like this. So, that is the challenges and prospects in the defect engineering of nanomaterials for catalysis. So, these are various nanomaterials, and various nanomaterials, these are catalytic nanomaterials, and what is their role in environmental remediation. So, that is TiO2 nanoparticles, composition is titanium dioxide, environmental application for water and air purification, and the key function is that they can photocatalytically decompose organic pollutants and toxic chemicals under light. So, they use light to photocatalytically decompose organic pollutants and toxic chemicals. Then iron oxide nanoparticles. So, various iron oxides can be used for environmental remediations. So, the type and composition can vary, Fe2O3 or Fe3O4, that is the iron oxide nanoparticle for environmental remediation, wastewater treatment and soil remediation. The key function is that it can degrade hazardous organic compounds and assists in heavy metal removal. So, it can basically degrade hazardous organic compounds and assists in heavy metal removal. So, the entire process I will be discussing in detail, that can be iron nanoparticles does that via Fenton reaction, that I will be discussing in detail in my later slides. So, zinc oxide nanoparticles, the type and composition zinc oxide, and it is helpful in water purification and sterilization. Key function is that it disinfects contaminated water and breaks down organic contaminants. Then silver nanoparticles. Silver nanoparticles are basically used for water and soil treatment. It exhibits strong antimicrobial action, neutralizes pathogens and harmful microorganisms. So, it is basically antimicrobial in nature. So, for fighting microbial pollution, you can use silver and nanoparticles. So, that's just a representation with microbes, heavy metals, hydrocarbons and pesticides. This much pollution is being caused by aldehydes and all. So a polluted environment and nanomaterials, and these filter out into a clean environment. So nanomaterials can be filtering these things into a cleaner environment, and mechanisms of reaction may be via adsorption, via a simple adsorption, or filtration. You just filter things out. See, you either adsorb things or you filter things out, or by oxidation, you are breaking your pollutants down via oxidation, or photocatalysis, you are breaking down something by the effect of light, and disinfection, you are killing microbes. Okay. So these can be the various mechanisms of reactions that nanomaterials use to turn polluted environment into a clean environment. And the types of nanomaterials, these are various and many. The mesoporous, the gold nanoparticles, these are the mesoporous silica or something, then gold nanoparticles, then lipids or polymeric nanoparticles, or liposomes or magnetic nanoparticles, membranes, hydrogels, fullerenes, dendrimers, nanotubes, and Q dots, quantum dots. So all these various types of nanomaterials, and there are many more. So these nanomaterials, basically they will be helping in filtering out a polluted environment to a clean environment. That's the same thing in detail. So polluted air and water to clean air and water via all this. There can be inorganic based nanomaterials. Okay, these are inorganic based nanomaterials. There can be carbon based nanomaterials. The graphene, graphite, fullerenes, carbon black, all these are carbon based nanomaterials, or the inorganic nanomaterials like metallic nanoparticles, or organic based nanomaterials. These are solid lipid nanomaterials, dendrimers, liposome, polymeric nanomaterials, micelles, all these are organic based nanomaterials. So all these types of nanomaterials, these can be used for turning polluted air and water to a clean air and water. So let's study the basic chemistry of catalysis. Catalysts basically provide an alternative reaction pathway. So it's like you are going from point A to B and taking a long route, and your catalyst will provide a shorter path, an alternative reaction pathway, so you will reach there faster. So your reactants are turning into products faster. So they are providing, catalysts are providing an alternative reaction pathway. But they do not do so by altering thermodynamic equilibrium. They do not alter the thermodynamic equilibrium. The thermodynamic equilibrium remains the same, but they are able to create an alternative reaction pathway. They are able to speed up the reaction. So all the catalysts do that. So this is the basic principle of catalysis, and catalysts do so by they provide an alternative reaction pathway. How do they do that? They do so by lowering the activation energy of the reaction. So what is the activation energy of a reaction? That we will be learning in my next slide. So they help in lowering the activation energy of a reaction, and surface interactions dominate the nanoscale catalysis. So as I have already told you that on bulk materials, the forces that are active are gravity and inertia, but in case of nanomaterials, the surface interactions that dominate, these are the elasticity, the surface tension, the electrostatic forces, the van der Waals forces. All these forces dominate more at the nanoscale. So these will also dominate the nanoscale catalysis. So these are the concepts that you need to keep in mind. Thermodynamics, when you are thinking about thermodynamics, the role in nanocatalysis is that catalyst does not change delta G or equilibrium. So catalyst is not changing the value of delta G, okay. So it is not changing the thermodynamic equilibrium, it is remaining constant. And activation energy, nanocatalysts are significantly reducing activation energy. So activation energy is being reduced. Then surface chemistry, as you know, the pollutants are being adsorbed on the surface. So more the surface area, more the adsorption and reaction and desorption. So this is the reaction that is taking place, and more is the surface area of the nanomaterial. So more is this process happening, okay. So this is how it depends on it. Then efficiency reason is that large surface area, defects and quantum effects. Activation energy in catalytic reactions. So what is activation energy? It is the minimum energy that is required to initiate a reaction. So you need some energy to start a reaction. You need to change something into something. You need to convert some reactants to products. You need a minimum amount of energy that is required to initiate that reaction. Okay. So that minimum energy is known as activation energy. So you can provide more energy, but there will be a certain threshold energy that is required to start the reaction. So that energy is known as the activation energy in catalytic reactions. So nanocatalysts stabilize reaction intermediates and they reduce the activation energy of the reaction. So reduced energy barriers, basically they enhance the reaction rate. So when you reduce the activation energy, the energy that is required to start a reaction, so obviously your reaction rate is going to go faster. So this can be explained by using energy profile diagrams. I will be showing that. So that is a comparative animated picture that is showing you how reactants are turning to products with catalyst and without catalyst. So as you can see, without catalyst the boy has to go uphill and down there to the products, and with catalyst it is doing that easily. So the activation energy will be lowered. It is he is not requiring much energy to do that because there is no uphill thing. So he is being able to do that sooner and faster. So that is the relevant energy in molecules, and this is the time. So this will this person who is sitting on a lower thing, he will be doing this more quickly with lower effort and energy, but this person he will be requiring more effort and more energy. So that is without the catalyst and this is with the catalyst. So that is just a comparative study. That is just that is just a picture to make you realize what actually activation energy is. So that is the actual graph of potential energy and reaction process. So your reactants are converted into products, and that is without the catalyst. The blue line is your energy required for the reactants to convert to products, that is blue is the activation energy without catalyst, and red is the activation energy with the catalyst. So you involve a catalyst in your reaction, and this red line is the activation energy that is required for the reaction to turn into products. So as you can see, this is higher, more energy is required in a reaction without a catalyst, more activation energy is required for it to initiate the reaction, for the reactants to turn to products, and with the catalyst this is lower. So that is delta H, the difference between these two activation energies. Now the degree to which nanocatalysts lower the activation energy is quantified by comparing the rate constants of the catalyzed and uncatalyzed reactions using a form of the Arrhenius equation. Okay. So this is the Arrhenius equation, and the degree to which nanocatalysts lower activation energy, you know how much you are dealing with a reaction without catalyst and you are dealing with a reaction with catalyst. So the reaction with catalyst, how much lower energy, activation energy did you need as compared to the reaction without catalyst, that is quantified by comparing the rate constants of the catalyzed and uncatalyzed reactions, that is by using a form of the Arrhenius equation, which is this, where K is the rate constant, A is the pre-exponential factor or frequency factor, EA is the activation energy, R is the universal gas constant, and T is the absolute temperature in Kelvin. So that is the inverse graph of it, this Arrhenius equation, and that is the slope EA by R, intercept, and this is. So how do you calculate the slope? You can calculate the slope from the log inverse relation of this Arrhenius equation. You calculate the slope by y is equals to mx plus c. So that is your slope, minus EA by R, that is your slope, and the c, that is your intercept. That is your intercept. So why do nanomaterials reduce the activation energy? They do so because of the high density of surface atoms. As I have already told you, there are more surface atoms in a nanomaterial than there are atoms at the core. So there is a high density of surface atoms. So these can act as catalysts far better because of their surface atoms. Then there are defect sites and unsaturated coordination sites. And then because of quantum size effects, there is an altered electronic structure, and then enhanced absorption of reactants. So they can cause enhanced absorption of reactants. So that's in detail how intrinsic properties of nanomaterials affect what difference the intrinsic properties of the nanomaterials is on its catalytic activity. So these are intrinsic properties of nanomaterials: a higher band gap, band structure, mechanical properties and magnetic properties. These are the binding energy density factors, and then these are the structural parameters, that is lattice parameters, atomic density and binding energy. These are responsible for the shape, size and interparticle distance effect. These are responsible for the composition and oxidation state effect. And then activation energy and phase transition, these are responsible for the support and confinement effect. So these are the effect of intrinsic properties of nanomaterials on its catalytic activity. So why do nanomaterials actually reduce activation energy? Because of high density of surface atoms. You can see that if there are more surface atoms, there are more active sites also. So defect sites are also greater and unsaturated coordination sites are greater. So reactive defect sites can be more. So they can also be tailored. Then quantum size effects, which causes altered electronic structure and enhanced absorption, that is a strong reactant binding. So all these make the nanomaterials reduce activation energy far more efficiently than other catalysts. So that's an energy diagram where nanomaterial is causing a reduced activation energy and reactants are turned into products. Mechanisms of pollutant degradation. So how do you degrade a pollutant with the help of nanomaterials? So adsorption of pollutant on nanocatalyst, the first step is the adsorption of pollutant on the nanocatalyst surface. So they have a very high surface area, this comes into a picture now, and your pollutants are getting adsorbed on the nanocatalyst surface. So formation of reactive intermediates. So your pollutants are now adsorbed on the nanocatalyst surface, and there will be a formation of reactive intermediates. Then electron or radical transfer reactions will occur, and then conversion to harmless end products. That is the schematic reaction mechanism in the Fenton process. So that reaction is known as the Fenton reaction, where you can see Fe3 plus being converted into Fe2 plus. Okay, so this is being converted into this, and your hydrogen peroxide is being broken down into O2 or OH radical in H2O. So this is how it is being broken down, your hydrogen peroxide. Basically hydrogen peroxide is used in the water cleaning process, and your nanomaterial is speeding up that process. So it is what it is doing is that it is breaking down H2O2 more efficiently, and these hydroxyl radicals, they are helping in degrading the pollutants to certain non-toxic products. So these are the intermediates, and then to H2O2, CO2 and degradation products. These degradation products are non-toxic products. So what happens in Fenton reaction? Your Fe3 plus gets converted into Fe2 plus, and because of which your H2O2 gets degraded and OH radical is released. This OH radical will break down your pollutants, make intermediates, and then into non-toxic degradation products and H2 and CO2. So that is how it works. The schematic reaction mechanism in the Fenton processes. Yes, see here you are basically, these are the organic sand, this is the catalyst, that's a polluted solution, and you are putting a catalyst in that. Then OH radicals are being released. You also put H2O2 into this, and then OH radicals are being released, OH radical generation, and then residual sludge. So the OH radicals, what will they do? They will be breaking down the pollutants, and organic oxidation will take place, and there will be this residual sludge and clean water. So you are taking a polluted water, you are breaking down with the catalyst, creating oxygen radicals, that is breaking down your pollutants into non-toxic degradation products. Then they are being settled over here as a residual sludge, and then you are obtaining clean water. That is a picture of decomposition of H2O to H2O and O2 catalyzed by platinum nanocatalysts, and it controls the energy yield of several energy conversion technologies such as hydrogen fuel cells. So this is how the reaction takes place, H2O2 into H2 and O2. So oxygen bubbles are also released. These oxygen bubbles will later be used in microbots also for propulsion process, and these are also used for hydrogen fuel cells. So either hydrogen gas or oxygen gas that is released that can help in that can be helpful in hydrogen fuel cells and all that can create oxygens in water, that can create water bubbles. So red is the chemisorbed oxygen, and that is the rate limiting step. Now let us discuss the photocatalytic degradation mechanism in detail. So light excitation generates electron hole pairs. As I have already told you that if a nanomaterial is being excited with the help of a light, it generates electron hole pairs. So formation of reactive oxygen species, then there will be a formation of reactive oxygen species which will help in the oxidative degradation of organic pollutants. Common materials, this is TiO2, zinc oxide nanoparticles. So that is a picture that will give you a clear view of this photocatalytic degradation mechanism of metal and organic contaminants. So that is light source, light coming from here, nanoparticles like CNTs, fullerenes or nanocomposites, these are nanoparticles. So the light falls on this, on any of these nanoparticles, and what happens is that from the valence band the electron gets excited, jumps onto the conduction band. So here hole is created, that is H plus, and these are the electrons. Okay. So these are the electrons, and now what will these do? These will convert H2O to OH radicals, which will be used for photooxidation process to convert organic contaminants to H2O and CO2, and this can be helpful in basically creating O2 radicals that will be helpful in creating Mn plus to Mn plus. Okay. So that is changing the valency of metal, and that is degrading the organic contaminants. That is a more detailed picture. You can see there is H mu to valence band, electron jumping over here, that is the band gap energy, that is H plus, O2 to O2 minus radical, which goes on to degrade organic molecule to degradation process. Or this H plus is also helpful in creating OH radical from H2O from water, and then that is also degrading your organic molecule. So your organic molecule is being degraded by O2 minus or OH radical and being converted into degradation products that are non-toxic. Then adsorption process in nanocatalysis. Adsorption is, as you know, the adsorption is the first step in catalysis. It can determine the efficiency and selectivity. So it is strongly influenced by surface chemistry, and there are two main adsorption types that I will be teaching you in detail. So types of adsorption. Your adsorption can be physisorption, where weak van der Waals forces interactions take place, or low adsorption energy and reversibility, or chemisorption, where strong chemical bonding happens, and high specificity and catalytic relevance. So what happens in physisorption is that you imagine that what physisorption is basically adsorption on the surface. So you have some material and something is being adsorbed on it on the surface. So that will happen with weak van der Waals interactions, and there will be no chemical bond formation. So the adsorption energy will be low, but in chemisorption what happens is that your strong chemical bonding is happening. So there is a high specificity because chemical bonds are highly specific. So in chemisorption there is a high specificity and catalytic relevance. So that is physical adsorption, where you can see that is the adsorbent, the surface on which your particles are being adsorbed. So that is the adsorbent surface, and that is the adsorbate or adsorbed. So this is being adsorbed onto this surface. This is known as physical adsorption. And in chemical adsorption there are binding sites. Okay, there are binding sites to which your substance will get adsorbed. So this is your substance that is being adsorbed to a binding site that is present on the adsorbent surface. So that is the energy diagram, and you can see for physisorption low energy will be required to break and make the bonds, while in chemisorption more energy will be required because as chemical bonds are stronger. That's a comparative graph. That's the nature of interaction. So in Physi's option, weak van der Waals forces dominate, while in Chemi's option, strong chemical bonding, either covalent or ionic bonding takes place. Bond strength is low in Physi's option, obviously, and in Chemi's option, where chemical bonds are formed, the bond strength is higher. Activation energy usually none or very low. So in Physi's option, what happens is that it usually does not lower activation energy much, but in Chemi's option often requires higher activation energy. So the requirement for Physi's option is that it does not require very high activation energy, but in Chemi's option it can require activation energy. So reversibility, Physi's option is easily reversible. What is sticking just on the surface, you can easily put it out, but in Chemi's option it is generally irreversible as the bonds have already been formed. So you will be needing more energy to break the bonds now. Temperature dependence. Physi's option can be favored at low temperature, while Chemi's option, where bonds are being formed, it is favored at moderate to high temperatures. It will require more temperature. Then layer formation can form multi-layers, usually monolayer adsorption. So Physi's option can be happening in multi-layers, but in Chemi's option, usually monolayer adsorption takes place. Then specificity, non-specific, weakly depends on surface. Physi's option is non-specific and it weakly depends on surface. It's a surface thing, so it is highly non-specific, and Chemi's option is highly specific and it depends on surface atoms and sites. So Chemi's option, as you know, chemical bonds are being formed, so it will depend on the surface atoms, whatever atoms are present on the surface. If there is a certain atom A, it will bind with atom B, so it will depend on atoms and sites on the surface, and it is highly specific. So if A binds with B, so it is going to bind with B only. So this is what happens when Chemi's option takes place. The specificity is very high. Effect on catalysis. Physi's option helps in initial pollutant capture and enhances surface contact. So this is important. What is the effect of catalysis? What is the effect of Physi's option on catalysis? It helps in initial product pollutant capture and enhances surface contact. So initially how pollutants need to be captured, it will depend on Physi's option, and it will enhance the surface contact. Chemi's option is essential for the catalytic reaction. So for the catalytic reaction, Chemi's option is being required. It enables bond breaking and product formation. Role of nanomaterials. In Physi's option, high surface area increases adsorption capacity. So what happens is that because of nanomaterials, there is a high surface area, so adsorption capacity is higher. And Chemi's option, high surface atoms, surface defects and active sites enhance strong bonding and reaction rate. So role of nanomaterials is that in Physi's option, high surface area increases adsorption capacity, and in Chemi's option, high surface atoms, defects and active sites enhance strong bonding and reaction rate. Then examples in nanocatalysis, temporary adsorption of gases before reaction, and Chemi's option, strong binding of reactants on TiO2, PT, AU and ZNO surfaces. So that's the picture of an adsorbent, and the material that is being used, the surface that is used for adsorption, and that is the adsorbate, the atoms that are being adsorbed on the surface. So there needs to be an adsorbent, the surface on which your adsorbates are being adsorbed. So adsorbent is basically the surface provider. This is the surface provider, and adsorbate is the substance that is going to stick on the surface. So that is the difference between adsorbent and adsorbate. It's important to remember this, as we will be discussing a lot about this. So adsorbent is the surface provider and adsorbate is the substance that is sticking. So the relationship is like a host and a guest. Okay. So host is the adsorbent and guest is the adsorbate. It has come over its house, interacting at the surface. Okay. So what is the relationship between adsorbent and adsorbate? Surface interaction. Adsorbent provides active surface sites. Your adsorbent will provide active surface sites, and adsorbate molecules will attach to these sites. Okay. So what is the relationship between adsorbent and adsorbate? In terms of surface interaction, your adsorbent will provide active sites. So, your adsorbent is providing a surface, and on surface there are active sites for adsorbing of the adsorbate molecules, and adsorbate molecules will come and attach to these sites. Then nature of bonding, this can be physisorption, that is weak van der Waals forces, or chemisorption, that is with strong chemical bonds, covalent or electrostatic, whatever bonds are there, these are strong chemical bonds. Then dependence on surface area. So, greater surface area of adsorbent means more adsorbate attachment. So, obviously if the surface area is more, so more amount of adsorbate can come and attach to that surface area. Nanomaterials are excellent adsorbents because of their very high surface to volume ratio. So, because of the very high surface to volume ratio, nanomaterials can come and adsorb very efficiently. Then concentration dependence, higher adsorbate concentration increases adsorption until surface becomes saturated. So, until your surface is becoming saturated, more and more adsorbate is coming and adsorbing to it, coming and sticking to it. So, higher adsorbate concentration increases adsorption until, so you put more and more adsorbate concentration, adsorption will go on increasing until the surface becomes saturated. It's like you keep filling something in a glass of water, you keep filling water till it goes on to the surface and it starts overflowing. So, there is a limited capacity of something. So, it is like that when your higher adsorbate concentration will cause an increase in adsorption only till the surface of your adsorbent becomes saturated. So, there is a limited capacity of the adsorbent, it depends on the surface area and on the active sites on that. So, if the active sites are all full, you cannot, your adding of more adsorbate won't do anything because the surface is already saturated. So, dynamic and reversible and irreversible. Physisorption basically it is usually reversible and chemisorption is often irreversible. So, obviously because physisorption involves physical bonds, so it can be broken down, it can be basically reversed. You can take off the substance that is adsorbing, sticking to the surface with physical bonds, while with chemical bonds it is often irreversible because you have to break the bonds. And thermodynamic relationship, that we will be studying in detail. It follows the adsorption isotherms like Langmuir isotherm, monolayer, or isotherm for multilayer heterogeneous surfaces. So, what are adsorption isotherms? Adsorption isotherms basically describe the relationship between the adsorbate and adsorbent. So, you can describe the relationship between the adsorbate and adsorbent graphically. These will create adsorption isotherms. So, adsorption isotherms have two types: Langmuir isotherm, that is for monolayer adsorption, for a monolayer single layer adsorption for homogeneous surfaces, and Freundlich adsorption isotherm is for heterogeneous surfaces. These are used to analyze catalytic performance. That is the definition of an isotherm. Adsorption isotherms describe the relationship between the amount of adsorbate adsorbed per unit mass of an adsorbent. The amount of adsorbate adsorbed per unit mass of adsorbent, that is QE, okay, per unit mass of adsorbent, how much amount of adsorbate is being adsorbed, okay, and the equilibrium concentration of adsorbate in the solution CE at constant temperature. So, that is the relationship between the amount of adsorbate adsorbed per unit mass of adsorbent and the equilibrium concentration of adsorbate in the solution, that is CE at a constant temperature. They provide insight into the adsorption capacity, surface characteristics and mechanisms of adsorption. Then Langmuir isotherm basically assumes monolayer adsorption. Langmuir isotherm assumes that there is a monolayer adsorption on the surface of your absorbent. So, on the surface of your adsorbent only a single layer of adsorbates are coming and sticking. So, there is a monolayer adsorption. That means adsorption occurs at specific homogeneous sites on the adsorbent. And once a site is filled, no further adsorption occurs at that site. So, Langmuir isotherm assumes that once a site is filled, no further adsorption occurs at that site. No interaction between adsorbed molecules. There is no interaction between the adsorbed molecules. So, all these are assumptions of the Langmuir isotherm, and that is the mathematical form where the QE is the adsorbed amount at equilibrium. So, this is the adsorbed amount at equilibrium. This will depend on maximum adsorption capacity of the material then Langmuir adsorption constant, that is KL, then equilibrium concentration, that is CE. So, it depends on this, like this. That is the graph of a Langmuir adsorption isotherm. So, you are adding your adsorbate molecules, and it is going on adsorbing onto the adsorption surfaces. So, that is the surface coverage. You go on adding the material and it is increasing and increasing until and unless your the surface of the adsorbent is highly saturated, all the active sites are saturated, and now it goes constant after this. So, theta is Kp upon 1 by Kp. That is the equation for it. The theta is the surface coverage. That is the Freundlich isotherm, where empirical provides the empirical model for heterogeneous surfaces. This is for heterogeneous surfaces. Adsorption sites have different energies allowing multi-layer adsorption. So, basically here the adsorption sites have different energies. As we are considering heterogeneous surfaces, they will have multiple adsorption sites with different energies allowing multi-layer adsorption. So, adsorption is not just happening in one layer, but it is happening on top of it and on top of it, like a multi-layer adsorption. So, this is not limited to a monolayer formation. The mathematical form can be QE is equals to KFCE, that is QE is adsorbed amount at equilibrium, then Kf is the Freundlich constant, and then 1 by n is adsorption intensity, and C is the equilibrium concentration. So, that is the mathematical form for this, and hence it can be plotted like this, which is almost goes like a straight line because the multi-layer adsorption is happening. So, you keep on adding adsorbate and it goes on being adsorbed on the adsorbent surface. So, this is the amount adsorbed, and you put on more adsorbates and more adsorption is taking place, more adsorption taking place because the adsorption is happening in multi-layers. So, that is Freundlich adsorption isotherm for you. Experimental data fitting in catalysis. So, I will be giving you an example of an experimental data fitting. So, experimental data is used to validate models. So, you will get an experimental data of let us say you create a adsorbent, a good material, and now you need to validate the data, how good an adsorbent it is. So, your experimental data can be used to validate models. So, reaction kinetics analyzed using rate equations. Your reaction kinetics can be analyzed using rate equations, and linear and non-linear fitting methods. I will be teaching that in my next lecture, and helps extract rate constants and adsorption parameters. So, that is an experimental data fitting, Langmuir and Freundlich adsorption isotherm models for the adsorption of chromium onto PAN, NH2 and nanofibers. So, these nanofibers are your adsorbent surface, these are providing your adsorbent surface, and this chromium is coming on as an adsorbate and coming onto this surface. So, it is like these nanofibers are providing a surface, that is your adsorbent, and this CR is coming onto it as an adsorbate, CR is coming as an adsorbate and getting adsorbed onto the surface of this adsorbent. So, that is the adsorption isotherm for it. So, you can see they have plotted, that is an experimental data fitting. So, that is the Freundlich isotherm, So, if you assume that there is a multi-layer adsorption, this would be your graph, and if you assume that there is a heterogeneous surface, so that will be Freundlich adsorption. Then you assume that it is a monolayer adsorption, and on a homogeneous surface, then you consider Langmuir adsorption, that is shown by this dash line. Then this shows the experimental data fitting, like for this experiment, this particular experiment, this is the isotherm. So, you can compare the models with this particular experimental data fitting, and you will know the inclination of the, in your particular experiment, which model it is following, and from that you can figure out if the surface is homogeneous or heterogeneous, and what kind of adsorption is taking place, a monolayer adsorption is taking place or a multi-layer adsorption is taking place. Then kinetic models for pollutant degradation. So, pseudo first order kinetics is commonly applied in the pollutant degradation mechanism, that I will be discussing in detail in my next lecture. Then rate constant reflects catalytic efficiency. Then Langmuir-Hinshelwood model for surface reactions, and then correlation between adsorption and degradation. Relevance to nanobiotechnology. So, bio-inspired catalytic nanomaterials are already being made, and enzyme mimicking nanozymes are already being made. They are used widely. And then green and sustainable remediation strategies, and nanocatalysts have been used to create green and sustainable remediation strategies, and integration of biological and inorganic catalysts. Summarizing the lecture, and now you can see that catalytic nanomaterials play a key role in remediation, and they do so by lowering the activation energy, enabling faster degradation. Then adsorption and surface mechanisms dominate. So, we have studied about the various adsorption isotherms, as adsorption happens on the surface, and surface matters a lot in case of nanomaterials. So, adsorption surface mechanisms dominate. Then data fitting validates catalytic performance. So, when you do data fitting for say a new experimental model, so that will validate its catalytic performance. So, as we can see that catalytic nanomaterials play a key role, a vital role in remediation. So, in environmental remediation, catalytic nanomaterials play a vital role because they have a high surface area, which makes them better adsorbents, and also they help in lowering the activation energy of the reaction. They act as catalysts, and they help, they enable faster degradation. So, we have also seen how these nanocatalysts can be compared with enzymes, and how they are more advantageous over the enzymes, because normal methods of, like conventional methods of remediation, they are outdated now, and you cannot be using enzymes on such a larger scale. So, we use these nanocatalysts which mimic those enzymes and perform far better. So, catalytic nanomaterials basically lower activation energy that enable faster degradation, and then adsorption surface mechanisms dominate. So, we have studied about the adsorption isotherms, how surface area of a nanomaterial increases and the adsorption start to matter more. So, there is it's like more the surface area, more adsorption takes place, and there are models for different adsorption processes, like if you need to know if it is a monolayer adsorption or it is a multi-layer adsorption. For a monolayer adsorption on a homogeneous surface, you plot the Langmuir isotherm, and for a heterogeneous surface and a multi-layer adsorption, you plot the Freundlich isotherm, and comparing these models, you can plot a data fitting which can validate the catalytic performance of a new material. Now, you like if you are making a new material, for determining its catalytic performance, you need to plot these isotherms and validate the performance of these nanomaterials. So, that is how you use catalytic nanomaterials for environmental remediation. Thank you. Thank you for listening.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way, considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally, even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used, and it became popular during World War II in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Danzig is considered the father who really proposed the technique of linear programming as a very nice tool, where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that, things have really moved very fast. They have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see, and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization and operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system and so on and so forth. In the coming years, it is thought and definitely with some positive viewpoint that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example you want to basically have a layout such that Minimization of cost is one factor, and the maximization of, say for example, benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously, it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add-on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.